begin by thanking the organizers for putting together this beautiful workshop. I really enjoy very much being in an in-person conference finally after such a long time. So this talk is going to be about hot QCD in electric fields. It's not going to be a lattice talk. It's going to be about perturbation, one-loop perturbation theory in QED, actually. So this is something very simple where you would think everything is solved already. And let's see what the talk is going to be about. It's in collaboration with Gergely and Marco, who is also there in the audience. Right. So it's containing gauge fields, and if you wait till the end, you will also see that it has to do something with topology. So I think it's suited for this workshop. I will begin with a brief introduction about why electric fields are interesting, and then we will discuss the most pressing issue. What does it mean to have equilibrium when we have electric fields? And I will tell you a couple of words how one can define equilibrium in this setting. And then we will look at two different ways to discuss this system, one due to Schwinger and one due to Weldon. And spoiler is that they are not going to agree with each other. And we are going to discuss this disagreement, both with perturbation theory and at the very end with, in a very brief way, on the lattice with imaginary fields. So in the context of strongly interacting matter, heavy ion collisions, off-central heavy ion collisions, we have very strong electric and magnetic fields generated in the early stages of the collision. They have some very non-trivial spatial profile, and they can lead to some very interesting effects in the quark-gluon plasma. And also in the context of QED, we have very large electric and magnetic fields generated in, for example, laser experiments or laser beam, electron beam collision experiments, which are planned currently. And there, again, you can reach up to very strong in this theory, marked by the electron mass squared fields, where you can have very interesting nonlinear phenomena that can be studied. When it comes to magnetic fields, then we understand a lot about both of these sectors. In QED, we know that the magnetic field, for example, leads to dynamical symmetry breaking. In QCD, it leads to an enhancement of chiral symmetry breaking. This is called magnetic catalysis. But we also know that at high temperature, that's not the case anymore. We have inverse catalysis, and we also know how the phase diagram looks like. I think you're going to hear more about this phase diagram in this workshop, actually. We also know how the equation of state looks like in the presence of magnetic fields that's marked by the magnetic susceptibility, which also has been calculated in different ways. So basically, all there is to know about this setup is at least qualitatively known, and there are some quantitative questions still remaining, but we know many things about it. And we know much less about electric fields. So let's come to this question of equilibrium in electric fields. And before I discuss that, a couple of preliminaries, just that we are all up to speed about what I'm talking about. Here is the vector potential from which you can get the electric and magnetic fields. They couple to the Dirac operator, in the Dirac operator, to the electric charges of the fermions. And an important point is that I'm taking the electric and the magnetic field as a classical background field. There is no back reaction from the fermions to the background fields, but they are classical. They are staying there as they are. Okay, it's important to keep this in mind. And then what I'm actually going to discuss is the leading response of the system to these electric and magnetic fields. They are the susceptibilities. And I'm always just looking at thermal effects. So this omega is the free energy, is the temperature dependent part of the free energy of the system. This actually means that there is no Schwinger effect in this discussion, because that drops out from this difference. So what about equilibrium? If you have a constant electric field in an infinite volume system, then there is no equilibrium, because the charges are accelerated and driven out to infinity, and there's just no way to get a setting where you have no currents flowing. There's always going to be currents flowing. But in order to define an equilibrium, we can get rid of one of these two assumptions, the constancy of the electric field in space or the infiniteness of the volume. If we assume that we have an oscillatory field in space, then here, for example, we have an electric field that points to the right, then here it points to the left, to the right again, and to the left again. That's the arrows in the orange region. And then the charges will move, the thermally existent charges will move towards regions of space where the electric arrows are pointing towards, and the oppositely charged particles will move in the opposite direction. And at some point, they will have this bluish distribution of charges. Then this situation is reached, and we have equilibrium because the forces locally balance each other. The forces from the electric field and the forces from repulsion of fermions. So degeneracy pressure. Notice I don't need dynamical QED for it. It is just the fact that fermions don't like to get very close to each other, as we all know from statistical physics. They are repulsing each other, and this leads to this kind of equilibrium. The same thing can happen if you are in a finite volume. Then you have a constant electric field, and then the charges accumulate near the boundary. But again, because you have a finite volume, there is going to be a charge profile, which looks like this. Notice that the two things are actually the same. If the wavelength on the left-hand side is very big, then zoom into this part, and you will see that it's the exact same as this one here. Okay, so if the wavelength is big, then we have equilibrium. We have maintaining equilibrium actually in the same way as we would do it in a finite volume. This picture is really important. I'm going to refer back to it all the time, so please try to memorize it. By the way, everything that I said so far can be understood in a really different setting. The barometric formula, which tells you how the pressure profile looks like in the atmosphere of the Earth. You assume a flat Earth, and then you have the gravitational potential, and then you look at how the pressure will look like as a function of the coordinate. And then you find the exact same picture, actually. The equivalence between the two pictures is that the gravitational force is the counterpart of the electric force. And here the atmospheric pressure is what can counterbalance the gravitational force. And in the other hand, we have the fermionic degeneracy pressure, as I just mentioned. An interesting analogy that you can think about. So let's calculate these susceptibilities once we have defined these equilibrium setups.
Can it be unstable?
Say again?
Can it be unstable?
Once you have defined an electric field in these kind of ways, there is one well-defined equilibrium which is reached, which is stable. But you need both the electric field and this peculiar charge profile. Whether the barometric is stable, well, I think we observe it to be. We observe it to be stable. So, susceptibilities, two ways to calculate it. One is, which I'm going to refer to with the Schwinger picture, is again gonna pop up all the time in the talk. He calculated in his very well-known paper in '51 the propagator for the fermion in the presence of the electric or magnetic background. Okay, this is going to be denoted by this double line, and then one can calculate the effective action, so the free energy with this. He did it at 0 temperature, and later on people also did it at finite temperature with 3 equivalent ways, but different ways: thermofield dynamics, imaginary Matsubara formalism, and real-time propagators. Okay, you don't need to know the details. This thing can be calculated, and subsequently you can expand it in the electric or magnetic field. That gives you the magnetic susceptibility and the electric susceptibility. This is my definition, or the Schwinger type of definition. It's not the only thing that you can do. You can do it the other way around as well. You can say that, okay, first, I'm expanding in the external background field, whatever background field that is. I'm saying I have some a mu of x, and I'm expanding in that. And I have always even number of external photon legs, 2 legs, 4 legs, and so on and so on. And then I'm evaluating it for a specific background. If I'm looking at the susceptibility, the second order thing, then I did this vacuum polarization diagram. And at 0 temperature, we all know from QFT how it looks like. At finite temperature, it looks more complicated because Lorentz invariance is partially broken. And then you have 2 different, form factors. Longitudinal photons and transversal photons behave differently. And Weldon showed how to calculate from these transversal and longitudinal form factors, the 2 susceptibilities. Okay, he did it actually for massless fermions. We are going to generalize this in a moment to massive fermions. So this is the Weldon way of doing it, which I'm going to refer to with the Weldon photo. And so notice this is a paper from '82, and the other approach is also dating then basically back to the '50s. Both of these approaches are very successful and famous, and they have been used for a whole range of industry, basically. Schwinger's approach has been used in Euler-Heisenberg Lagrangians to discuss a whole range of interesting phenomena for laser physics, a couple of references there, as well as also for thermodynamics in QED or models of QCD, mainly for non-zero magnetic fields. And it has been used in a, I don't know, plethora of ways. Weldon's approach is used typically in a slightly different context, mostly in QGP physics. And because it was then generalized to hot QCD, basically, this perturbative approach. And it was basically the basis of the hard thermal loop approach. It has been used in QGP transport, quark-gluon plasma, photon emissivity, and so on. So quark-gluon plasma physics. So the point what I would like to make here is that these two approaches are very famous and very well known. And nevertheless, the spoiler that is going to come out from this talk is that they don't give the same answer for a specific quantity, the electric susceptibility. For the magnetic one, they give the same, but not for the electric. Let's dig deeper into this and do this calculation a la Weldon in the massive case. So we consider an arbitrary background field, a mu of x, as I said. It is then better to go over to momentum space. So we have a mu of k. And then we follow Weldon's definitions relating the longitudinal and the transversal part of the photon vacuum polarization diagram to the electric and the magnetic susceptibilities. And we want the constant field. So we want to take this wavelength to infinity. That's sorry, the wavelength to infinity, so the momentum to zero. So notice then this is exactly the picture that I have. Go away. It doesn't go away. So this is exactly the picture I showed you earlier. We assume an oscillatory background, and then we take the limit where the wavelength goes to infinity. This is exactly how we calculate these susceptibilities in this picture. This is how the diagram looks like. And I mean, all of you have calculated such diagrams. Now we are at finite temperature. So you have to take not just the Fermion propagator, but it is complemented by the finite temperature part. Some of you might have calculated with these kind of propagators already. It's slightly more complicated than the zero temperature part. And here is the result. The way to do is to do the zero frequency limit, then do an integral over the momenta, temporal and spatial part, take the limit where the wavelength also goes to infinity. There's some caveats about how to do the epsilon zero limit, which is the Feynman propagator epsilon. And then subsequently, one can do finally a high temperature expansion. If you have any questions about this, Gergely Marko is the person to be asked because he's an expert on such high temperature expansions. This is the magnetic susceptibility. It looks like this, has a logarithmic term and subleading terms, and this is the electric susceptibility. It also has such logarithmic terms, but notice it has terms these green terms, which are actually divergent when you take k to zero. They blow up. You can also see that when you set the quark mass to zero, the Fermion mass to zero in the first place, then you're actually missing some logarithmic terms, which is what Weldon also missed in his calculation. Here it is in a slightly different form. I recognize that this zeros or this 1 over k squared term is actually coming with a coefficient, which is the Fermion number susceptibility. It's the second derivative of the partition function with respect to a chemical potential. You might see this here. It comes with t squared over 3 and m squared over some coefficient. This is exactly the number susceptibility. Let me show you the results from the Schwinger approach as well, which has been calculated in these other approaches. For the magnetic susceptibility, it gives exactly the same result. And for the electric one, it gives this result. And you can see it differs from the Weldon result in two pieces. There is deviation number 1, exactly this green term. It is present in the Weldon calculation and absent in the Schwinger calculation. And there's a deviation number 2. If you spot it here, the differently colored plus minus ones, there is a finite difference between the two terms as well. So the rest of the talk is about deviation number 1, where I think I can give you a satisfactory understanding why it is there. And for deviation number 2, I don't have any explanation yet.
But there is any way that they can compensate for this deviation? No, of course. No way.
They are different order in 1 over k squared, so they can't, but we will see. I will have a hunch about what it is related to. So deviation number 1, we have to go back to this equilibria. I told you that there is equilibrium if you have such a charge distribution. So of course, charges are accelerated, and at some point, this kind of equilibrium is reached. So if we have such an equilibrium, that means that there is a charge, a non-zero charge, local charge density, which we can describe with the local chemical potential, for example. The way that the Weldon approach works is that this derivative with respect to the electric field is evaluated at 0 chemical potential. I never spoke about the chemical potential. So far, it has been 0 actually. But we see that this is not really what happens. If we have an infinitesimal electric field, we will have an infinitesimal charge distribution. So keeping the chemical potential 0 is not really corresponding to this equilibrium definition. So let's try to define a derivative along local equilibrium. Okay, that means I have a particle number, an electric field dependent particle number density, which is such that the chemical potential coming from it exactly cancels the effect of the electric field. It's a little bit hard to digest, but my point is that you have to do something with the chemical potential to achieve that the derivative is along such equilibria. And if you do that consistently, you find that it cancels exactly this green term. Okay, I don't show, this is now very, very sketchy, but you have to believe me at this point. The result of this discussion is to exactly cancel this 1 over k squared term. So we can define an equilibrated version of Weldon, which now almost agrees with Schwinger, except for this plus minus 1. And as I said, at this point, unfortunately, the story ends, at least from my perspective. I can't offer you a good understanding of where this plus minus 1 comes from. But let me make 2 comments. The first is that in the case of the Weldon approach, we have to fulfill this equilibrium construction somehow by hand. And in the Schwinger case, it is, for some reason, fulfilled automatically, inherently. The Schwinger approach already knows that at finite electric field, there is this equilibrium setup, and the derivative is done along these equilibrium setups, which is, I find, very astonishing. And the second is that nevertheless, there is some regularization of this infrared divergence in both cases. And apparently, the 2 regularizations are not the same. They differ exactly in these 2 plus minus 1 different things in these finite terms. Maybe we can get back to this in a moment. But now let's move to a slightly different point, namely.
Sorry, this would suggest that if you do it in some other regularization, you can get any number there.
That's a very good question, and I fear the answer is yes. But yes, I mean, the way I see, there is a divergent term which you have to subtract, and that leads you to some. I mean, if it would be an ultraviolet thing, then that would be a scheme dependence, right? This is now an infrared divergence, suggesting that there is some infrared scheme dependence, which is manifested by the difference here. But I don't want to make a very strong statement because I don't fully understand where this comes from.
Yeah, but indeed, at high temperature, they start to stay.
You notice that at very high temperature, they are the same. But if you look at their difference, actually, this is not the case. So let's take this with a grain of salt. So this has all been Minkowski spacetime, and everything is real and so on. Now let's move to imaginary electric fields. And that is relevant for our lattice simulations. And we will see that the same divergence actually pops up in the imaginary field discussion on the lattice in some very, very particular way. So let's see how. We are doing the Wick rotation to Euclidean space. You all know that the chemical potential picks up a factor of I in that case. So in Euclidean space, it is natural to work with imaginary chemical potentials, and in the same way, it's natural to work with imaginary electric fields. You have 2 options. You can discuss or implement constant, so spatially constant magnetic fields or spatially constant imaginary electric fields on the lattice in a finite volume, and that leads to flux quantization. The magnetic field cannot be arbitrary. It can be 2 pi times some quantum. The imaginary electric field in a constant case cannot be arbitrary. It can be 2 pi times some other quantum, okay? This is how constant fields work in a finite volume. You can also do oscillatory fields. So this is sort of Schwinger and this is sort of Weldon. You can do oscillatory magnetic or oscillatory imaginary electric fields. Then you have an arbitrary coefficient, arbitrary amplitude, but then the wavelength is of course discrete because of the finite volume. So you can fit in a discrete wavelengths into your lattice. And here is the case for the magnetic field. So the red dots, so on the horizontal axis I have the magnetic field, the vertical axis is the effect of the magnetic field on the free energy, and this is the free case. I diagonalize the free Dirac operator, so I have the result exactly. And the red dots are the homogeneous magnetic fields. They come in discrete points, right, because of flux quantization. And the lines here, there are 3 lines, if you can see it, they are the different wavelengths. 3 fitting into my volume, or 2, or just 1. And if you can see it, they actually really go on top of the red dots. Okay, so having constant fields or oscillatory fields approaching a constant profile turns out to be the same thing in the magnetic field. So everything works as expected, and we understand everything. So the 2 approaches are exactly the same. Let's make sure that you understand this plot, because sort of people were nodding so far, and now there are not so many people nodding anymore. So maybe there's questions later on. In order to do the same thing with the electric field, I have to make a little detour. And the detour is again about the chemical potentials, so about the density, local densities. And if you are at finite temperature, then you have a gauge invariant object, the Polyakov loop. It's a local Polyakov loop now, so P depends on the coordinate in which the electric field points towards. And we can discuss the 2 setups, the homogeneous and the oscillatory field setups. In the homogeneous setup, the Polyakov loop, the U1 Polyakov loop looks like this. It's exactly this flux quantum which appears in it, and just depends on the coordinate. Notice that this local Polyakov loop makes a full turn as you go along the lattice. When x1 goes from 0 to L, it makes a full turn. So it makes a full turn around the U1 circle. This is this brownish line. Okay. On the other hand, the oscillatory field, it looks like this for the local Polyakov loop. It doesn't do a full turn, it oscillates. It goes first somewhere and then comes back and then comes back again. Okay, it's a sign. This is the purple line. You might remember this picture already because it was shown exactly in the talk by Gergely Marko the other day in the completely different context of the flatness of the effective potential. Actually, it's exactly the same thing. And this is where topology comes into the game. We see that the homogeneous field is topological. It goes around, it wraps around the U1 circle once, and the oscillatory doesn't wrap around the U1 circle, but it just tries to wrap around it, but turns around all the time. And now the important point, if you include not just the electric field, but also an imaginary chemical potential that shifts your starting point along this U1 circle. For the purple, it does something because the oscillation is now happening along a different point of this U1 circle. But for the homogeneous, it doesn't do anything because you are anyway doing a full circle. Where you start, it doesn't make any difference. Okay, Donnie is nodding. So what can we conclude from it? We can conclude that as soon as you have a homogeneous electric field, there is no dependence on the chemical potential. And this is indeed what happens. So on the right-hand side now, I'm showing the free energy due to the electric field as a function of the imaginary electric field. Again, red dots are the quantized values. And you see that the results are completely different from the magnetic case. Here this point is at 0, and here the other points at non-zero electric field are completely shifted from it. And if I also mark the chemical potential dependence, then at 0 electric field, as we all know, we have a dependence on the chemical potential, which is marked by this dashed area. But at every non-zero value of the electric field, there is no chemical potential dependence anymore. Notice also that these points here, they approach the vertical axis in the infinite volume limit. The larger your volume, the smaller electric field you can do. Nevertheless, there is always 0 chemical potential dependence. So I think this is really fascinating. Somehow the chemical potential dependence, which is there at 0 electric field, as we all know it, disappears as soon as you get an infinitesimally small electric field. So I think this is the most important statement from this part of the talk that I would like you to remember. And now, of course, comes the question, how is this realized with the oscillatory setups? So here are now the oscillatory setups. They are continuous in the electric field variable because now the electric field amplitude is continuous. So obviously they have to connect back to 0 smoothly. But you see, there is a very large dependence on the wavelength. As the wavelength goes to infinity, so the frequency goes from 3 to 2 to 1, somehow this line tries to collapse onto these red dots. How? Well, we can try to look at the chemical potential dependence. Now things become a little bit busy, but now you can do an oscillatory setup for different chemical potentials. And then you see, you map out this whole range that is usually there at 0 electric field. And as you decrease the wavelength, as you increase the wavelength, decrease the frequency, then these things try to sort of collapse onto this mismatch, which is there between the 0 and infinitesimally small electric fields. So I think this is really crazy that free fermions can give rise to such complicated behavior when you also consider background fields and chemical potentials. And I think I'm coming to, I have one more slide so that you also see something from full QCD. One can use the same approach with the oscillatory fields, not just for the free case, but for full QCD. And here are some details of our actions. Here is some, the definition that you can again use from the transversal and longitudinal vacuum polarization tensors. And just a tiny detail, these quantities that we measure here are actually exactly the same that Zoltan was talking about yesterday in the G-2 talk. Just we have to evaluate them at finite temperature. They are the same vacuum polarization type of diagrams. So it's an interesting observation that one can make that this is actually the same object, but at finite temperature. And here are the results. The dots are the results for the magnetic. This is the blue, and the electric, which is the red, up to a minus sign. And the two dashed lines are these perturbative predictions that I just discussed so far. I just had to go from pure QED to QCD. That meant changing the beta function coefficient slightly and including some strong coupling corrections. But the results seem very on top. Right, if I still have some time, then I can make more comments about this plot. So if you look especially at the magnetic susceptibility, it is something that you might find surprising, because this comparison of QCD results to perturbative results, for example, for the pressure of QCD, are known to be very, very different, right? You know that at 300 MeV, you are still very far away from perturbation theory. You have to go to, I don't know, 2 GeV or 1.5 GeV to see really an agreement. And in this case, the background field response is already very well described by perturbation theory at these low temperatures. This is just a peculiarity of QCD and QED physics combining with each other. So let's summarize. I think I made two important points that I would like you to remember. The first is that there is equilibrium with electric fields, contrary to what maybe most of us would have expected, but it involves non-trivial charge distributions. Okay, and apparently there is different and then there is a divergence, an infrared divergence, which pops up in the response with respect to electric fields that has to be regularized. And apparently the Schwinger and Weldon ways regularize it differently. Both of them get rid of the infinite term, but they still differ in a finite term, which, as I said, I can't really explain at this point in more detail. And the second point I want to highlight is how this whole thing is translated to the lattice when you have imaginary fields. And there we have this very involved way of how the chemical potential dependence is re-emerging. At non-zero electric fields, we have no chemical potential dependence. And as we approach back to zero electric fields, somehow it comes back again. And this happens in this very strange way. And that's it. Thank you very much for your attention.